Question 1. How many moles of O2 are consumed in the complete combustion of 11.5 grams of ethanol? So we're given this unbalanced equation, which is important because we have to balance it before we do any sort of further step with this problem. So let's start by balancing the equation. So a good way to start with balancing these equations is to locate one atom that only appears once on each side. So in this case, we can start with carbon, since we just see carbon in this liquid ethanol and in this gaseous carbon dioxide. So that's our only source of carbons on both sides of this equation. So we can just kind of trial and error it from there. So if we say let's put 1 in front of the ethanol, then we have 2 carbons on this side of the equation, and we have to have an equal amount of carbons on this right side of the equation. So we can put a 2 here so that it's equal. And now we can kind of look at hydrogens and oxygens. So I feel like starting with hydrogens. So let's see, on this left side we have 1 times 6 is 6 hydrogens. On the right side we have multiples of 2 hydrogens. So that's fine, because if 6 and 2, they're both even, so we can make a full multiple. So we can just write 3 in front of here, because 6 equals 3 times 2, or 1 times 6 is 6 hydrogens on the left side, and then 3 times H2O, there would be 6 hydrogens on the right side. And now we can move on to oxygens. So if we distribute these coefficients to each of these oxygen atoms, we will get that there's 1 oxygen from this ethanol on the left side. We have 4 oxygens from this carbon dioxide on the right side, and we have 3 oxygens from this water on the right side as well. So this side we have 7 oxygens total, and this side we have 1, and then we need to make 6 more. So that's fine, because we have this O2, and that means that multiples of 2 could work. And 6 is a multiple of 2, so we can just put the coefficient 3 in front of that, and now the equation should be balanced. So I'm going to erase this. So now that the equation is balanced, we can do a little bit of dimensional analysis to figure out how many moles of O2 are consumed. So whenever we do that, we want to start off with the mass and then convert it into moles, so that we can use the molar ratios from the balanced equation to figure out how many moles of another reactant or another product is going to be used or going to be produced. So in this case, we're starting off with 11.5 grams of ethanol, so we can write 11.5 grams of ethanol. And by the way, this is just the same thing as this, but it's just how I prefer to write it. And we can multiply this by 1 mole of ethanol and its molar mass, which you can calculate on your own, but I just looked it up, and it's 46.07 grams of ethanol. And we're asked how many moles of O2 are consumed. So we need to use this molar ratio between ethanol and oxygen on the left side. So we see that we have 1 mole of ethanol to 3 moles of oxygen. So we can do that. We can write 3 moles of oxygen over 1 mole of ethanol. And we can just stop there, because we're asked for the moles and not for the mass in grams of the oxygen. So a good way to check that we did this step right is to make sure all of these units cancel. And in fact, it does cancel, so we're just left with moles of oxygen, or O2, as our final units. And if you plug all of this into a calculator, you're going to get something like 0.75 approximately moles of oxygen. So that looks like answer A. Question 2. Thallium-201, a radioactive isotope used to image the heart, has a half-life of 3.05 days. How long would it take for a sample of thallium-201 to decay to 18% of its original activity? So this is a classic half-life decay question, and if you remember, half-life decay follows first-order kinetics. So there's a specific equation that is associated with that. So that equation looks sort of like this, where we have the ln, or the natural log, of the concentration or the amount of A, or just the compound at time t, is equal to negative kt, which k is the rate constant, time is the amount of time, plus the natural log of A at time 0. So the concentration or the amount of the substance at time 0, or initially. On your equation sheet, it might look a little different. I think it's like NT and NO, but it's the same thing. It's the same equations, just kind of rearranged in a different format. But this is the way I remember it, so I'm gonna show you how to do it this way. Another thing we need to note is the half-life equation. So on your equation sheet, you'll find that the half-life is equal to ln of 2, or approximately 0.693, divided by the rate constant k. And if you rearrange this, you get k is equal to ln of 2 over the half-life. So these are the two main equations we will need to solve this problem. So we're given the half-life, and we need to put this half-life into this k equation to find the rate constant k, and then basically use that to find the time at the time that it takes for it to decay to 18% of its original activity. So let's do that. So if we plug in k equals ln of 2 over 3.05 days, we will get approximately 0.22726, and then we can plug it into here. So ln of 0.18, because we're given a percentage of 18%, is equal to negative 0.22726 t, which is our unknown, plus ln of 1.00, or 100%. And this is actually very nice because it cancels out to 0. And the reason we use ln of 1 is because we start off with 100% of thallium-201, right? And then it slowly decays. So we're looking for basically how long it's going to take for there only to be 18% of it left. So now that we established that ln of 1 is 0, this equation simplifies a bit, so we just have to deal with this side of the equation. And if you rearrange that and plug it into your calculator, you should get that t is approximately equal to 7.5 days. So that looks like answer choice D. 3. Fluorine-18 is one of the radioactive nuclides used in positron emission tomography, PET scans. Fluorine-18 can be synthesized by bombarding oxygen-18 nuclei with hydrogen-1 nuclei, and we're given this equation, and we're asked, what is the identity of the other product X in this reaction? So for nuclear equations and those sort of problems, it's pretty much just a very simple algebra problem in disguise. So we want the top numbers on each side to match, and we also want the bottom numbers on each side to match. But we're not given all of the information yet that we need to solve this problem, so you will need to check your periodic table for this. We're only given these mass numbers, but if you look on the periodic table, you'll find that the atomic number for oxygen is 8, the atomic number for hydrogen should be 1, for fluorine it should be 9. So now we have all of the sort of requirements that we need to solve this problem. So we see that we have 18 plus 1 for the atomic or the mass numbers on this left side, which means that we have 19 on the top here, and we also need to make 19 from the top numbers of the right side of the equation. So 18, 18, 1, and 1. So this means that X has, or element X has a mass number of 1. So that there's 19 on both sides. And we do the same process for the bottom, or the atomic numbers on each side. So we see that 8 plus 1 gives us 9 on this side. We have 9 on this side. And the only way to make these match is if X has 0 as its atomic number. And in fact, this matches up with neutrons because neutrons have a mass of approximately 1 atomic mass unit, but it doesn't have an atomic number because atomic numbers are based on protons only. So that should give us a hint that it's a neutron, so the answer for this problem is D. 4. Calculate the energy in kilojoules per mole of 1 mole of blue photons with a wavelength of 473 nanometers. So for this problem, there's a handy equation that's given to you on your equation sheet. The equation for energy is E equals hv, which is also equal to hc over lambda, and h in both cases, this is Planck's constant, which is 6.626 times 10 to the negative 34. And lambda is supposed to be in meters, so to convert this to meters, we just multiply it by 10 to the negative 9, because nano and, nanometers. C is the speed of light, which is 3 times 10 to the 8. And then, we can just plug it in and find the energy for 1 photon. Not 1 mole, but 1 photon. And that's important later on. So when we plug everything in, we get 6.626 e negative 34 times speed of light divided by 473 times 10 to the negative 9. And we're going to get something about 4.2025 times 10 to the negative 19. And this is in joules because the units for Planck's constant and everything else is going to yield an energy in joules, and it's joules per particle, or photon. So particle, or joules per photon. But we're asked for 1 mole of photons. We're not asking for just 1 photon in particular. The question wants us to find the energy of 1 mole of photons. So we need to do a bit of dimensional analysis first to convert joules to kilojoules here. And then second of all, we have to convert it to find the energy of 1 mole from just 1 particle. So to do that, we could start off with what we got from this energy equation. So 4.2025 times 10 to the negative 19 joules per photon, or technically it could just be any particle, but for this question in particular, we're dealing with photons. And the conversion rate for kilojoules to joules, or vice versa, there are 1,000 joules in 1 kilojoule, so we can write that down. And there are 6.022 times 10 to the 23 photons in 1 mole of photons, or particles in 1 mole of particles in general. So that's Avogadro's number, so we can write that down as well. And now, just to check that we set up our dimensional analysis equation right, we can just try and see if all of these cancel out to give us this desired unit of kilojoules per mole. So we can cross out the joules, we can cross out the photons, and we get kilojoules per mole. So if you plug all of this into a calculator, you're going to get 253 kilojoules per mole, and that looks like option D. 5. A ground state hydrogen atom absorbs a photon of wavelength 92.62 nanometers. What energy level did the electron reach? So in this question, we're given a wavelength, lambda, and we're asked to find the energy level that this atom is reaching. So that's going to be indicative that we can use the Rydberg equation. And that looks like 1 over lambda is equal to the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. And in this case, n1 is going to be our initial state, and n2 is going to be our final state. In this case, since we're dealing with a ground state atom, this just means n1 is equal to 1. So this whole thing is equal to 1. We also have to convert this nanometers to meters, so we just multiply this by 10 to the negative 9. And the Rydberg constant, R, is equal to 1.096776 times 10 to the 7 in SI units. I don't particularly remember what the exact SI units are, but they're on the equation sheet. But just as long as you convert everything else to SI units, you should be fine. So we can plug all of this into this equation. So you get 1 over 92.62 times 10 to the negative 9 is equal to the Rydberg constant times 1 over 1, or just 1, minus 1 over n2 squared. So we could do a bunch of rearranging and whatnot, and just plugging things into the calculator. And once you do that, you should get that n2 is equal to 8.0097, or around that, which is approximately equal to 8. So our final energy level of this electron is 8. So that's answer D. 6. In an atom, how many total orbitals are there with principal quantum number n equals 4? So we have 4 different types of quantum numbers. N equals 4 just corresponds to period 4 on the periodic table. So essentially this question is asking us how many SPDF blocks have we passed once we get to the end of period 4 on the periodic table. So you could count through all of those and then figure out how many total orbitals there are, or you can do a trick. So knowing quantum numbers, the next one that comes after n is L, and that's going to correspond to the orbitals. So remember that L, the possible numbers are n minus 1. So in this case, 4 minus 1, which is 3. And in this case, you also have to remember that they kind of go in order. So 0 corresponds to the s orbital, 1 corresponds to the p orbital, 2 corresponds to the d orbital, or the subshell, and then 3 corresponds with the f subshell. And each of these has their own number of orbitals and numbers of electrons. So s, we have 1 orbital and 2 electrons. For p, we have 3 orbitals and 3 times 2, which is 6 electrons. For d, we have 5 orbitals, which is times 2, that's 10 electrons. For f, we have 7 orbitals. Multiply that by 2, we have 14 electrons. So in this case, we're just asked how many total orbitals. So we're not asked electrons, we're asked orbitals. So we just kind of add all of these numbers up. So you add these up, 1 plus 3, that's 4. 4 plus 5, that's 9. And then 9 plus 7 is 16. So if we add all of these, we get 16, which is choice D. Which set of quantum numbers n, l, m sub l, and m sub s is invalid? So this question is a lot like the last question, so I guess it's probably a good idea to start off by listing some of the constraints for these quantum numbers. So we know that L can go from 0 to n minus 1. We know that m sub L can be from negative L to positive L, and 0 is included in that. And then for m sub s, it's always going to be plus or minus 1/2. And that's because when we have an orbital, like any sort of orbital, the electrons are always going to fill like this. So we're going to have one that's going sort of up in this direction, and another one going down in the other direction. So that's why one of them is going to be positive 1/2, and one of them is going to be negative 1/2. So now we have these constraints, or these ground rules in mind. We can look through all of these answer choices and figure out which one does not follow these rules. So starting with A, we see that n is equal to 1 and L is equal to 1. And this already strikes a red flag because we've established that L can only be 0 up to n minus 1. So for a quantum number n equals 1, L can only be 0. So right off the bat, we already know that this answer is going to be A, but we can go through and evaluate the rest just to make sure nothing else is invalid. So going to this next quantum number for m sub L in option A, it is okay because we previously established that L can only be 0 in this case, right? Because n is 1, so L has to be 0. And then M sub L has to also be 0. And M sub S is negative 1/2, so that's fine. For B, N is 2, L is 0, so that's within 0 to 1, so that's fine. M sub L is also 0, so that's fine. And we have positive 1/2 for the spin, and that's also fine. And you can just do that with the rest of these, and you'll find that the other choices don't really violate any of these quantum number rules. So the answer is just A. Question 8. Which of the following properties is the following order of atoms from least to greatest incorrect? So for this problem, it's probably a good idea to start by drawing out all of these periodic trends that are listed as answer choices. So starting with A, we have the atomic radius. Atomic radius is going to increase from right to left and increase from top to bottom. And it increases from top to bottom because as we go down the periodic table, we're continuously adding more and more electron shells. And those shells are very, they have a pretty large radius. So there's going to be a pretty big increase from one period to the next. So that's why it's going to increase down the periods. And then for this other thing, for left to right or right to left, it's going to increase from right to left and decrease from left to right. And the reason is pretty similar to what we just said for top to bottom. So let's say that we have sort of like the same electron shell number. So let's say we have n equals 1, or we're just looking at the first period. All of the atoms in period 1 have 1 electron shell. So in that case, it's just hydrogen and helium, right? So helium is over here, hydrogen is on this left side. However, helium has more protons, but the same number of electron shells as hydrogen. So they both have 1 electron shell, but helium has 2 protons, whereas hydrogen only has 1. So there's going to be a greater force of attraction on the right side of the periodic table, because for the same number of electron shells, there's more protons. The additional number of protons is going to have a stronger attractive force to the electrons, which decreases the radius on the right side. The second sort of periodic trend we're looking at is B, or first ionization energy. This one is pretty straightforward. If we have a periodic table like this, we see that the first ionization energy is going to increase this way from left to right because we have the noble gases on the right side. And obviously noble gases they have full octets, and it's very hard to pull away an electron from a noble gas because it's very happy with its stable full octet. And similarly to the radius, to what we established with atomic radius, the first ionization energy will increase from bottom to top, and that's because on this first period, or as we go up the periods, we have a smaller radius, and the smaller radius causes greater attraction between the positive protons and the negative charge of the electrons. And that means that it's going to be harder to pull the electrons since the protons are closer to them and exert a greater force of attraction. The next sort of periodic trend we're looking at is C, which is non-metallic character. This one it sounds kind of weird, but the way I like to think of it is if we have a periodic table like this, all of the nonmetals are sort of in this triangle over here. So it's kind of going to increase in non-metallic character up this way. So it's going to increase from left to right, and it's going to increase from bottom to top. And then the last one for electronegativity, just sort of the same thing. I kind of don't really have it memorized, but basically, you know that oxygen and fluorine over here on this top right side, and those are sort of like two of the very electronegative atoms that I remember. So in the same sort of way that we just went through the non-metallic character, we can see that electronegativity is greatest on this top right corner. So it's going to increase this way, or sort of like increase from left to right and then increase from the bottom to the top. So now looking at all of these periodic trend tables we've drawn, it's pretty obvious what the answer is. It's kind of just like which one is not like the others. So all of these increase diagonally from the bottom left corner to the top right corner, except for the atomic radius. So that gives us a good hint that the answer should be A, that the following order of atoms is incorrect for atomic radius. So the answer should be A. Question 9. Which of the third period elements below has the successive ionization energies shown below? So for this question, we just kind of need to look at where is the biggest jump in the ionization energy. So in this case, we can see the ionization energies on this right side of this table, and it looks like the jump from 2 to 3 is going to be the biggest. So that gives us a pretty good hint, because basically if we see a jump, the biggest jump from ionization energy 2 to 3, it means it's a group 2 element. That's because, like, let's say we have beryllium, right? This is a group 2 element. So the first jump is going to turn beryllium kind of isoelectronic with lithium. That's okay, that's fine. It's not going to be too hard because beryllium doesn't really have a full octet, and so it's going to be relatively easy to strip away that first electron. The second ionization energy is going to be also not that hard because we're going from lithium and turning it into isoelectronic with helium. That's good, that's fine, because helium is more stable, it has a full octet. Lithium can afford to lose that one electron, so it's going to be pretty happy doing that. But then if we try to do this again and we try to strip away an electron from helium, that's going to be a lot harder because helium is a noble gas and it's very happy, it's very stable. So it's going to take a lot of energy to go from helium to isoelectronic with hydrogen. So that's why group 2 atoms have the biggest jump in ionization energy from IE2 to IE3. So basically what this question is asking is which one of these period 3 elements is also in group 2. So let's just take a look. Sodium is over here, that's not it because that's in group 1. Magnesium looks like it's in group 2. So that's probably our answer, but going down the list, aluminum is here, which is in group 3, so that's not it. Silicon is in group 4, so that's not it. And phosphorus is in group 5. So the only answer here is going to be B, or magnesium. Question 10. A system releases 118 calories of heat to its surroundings and does 332 calories of work on its surroundings. What is the change in internal energy of the system? So this problem is basically just addition, but the important part that we don't want to trip up on is the signs. So whenever we are doing work, or if a system is doing something and it's going to the surroundings, whether it's work or releasing heat energy or just energy in general, this is going to be negative because we're losing energy from the system and the surrounding is gaining energy. And then in the other direction, if the system or if the surrounding is doing stuff to the system, it's going to be positive because the surroundings are losing energy and then the system is gaining it. So with that in mind, we can kind of assign plus and minus signs to this to the numbers in this problem and then add them together to get our answer. So we're seeing that a system releases 118 calories, and this keyword is release, which means that the system is losing 118 of calories to its surroundings. So we're going to write 118 calories, and then similarly, let's look at this. The system is doing work on the surroundings. The surroundings aren't doing work on the system is doing work on the surroundings. So that matches with this, and that's also going to be negative. So then it's going to be 118 calories plus 332 calories, but they're both negative, so it's just going to be the negative. And if you add these together, you'll get negative 450 calories. So our answer is E. Question 11. For what in its standard state at 25 degrees Celsius, the enthalpy of formation is 0? This is just an element, and I'm not really sure how to explain that other than just saying that this is the definition of what standard state means. So the answer for this question is A. Initially at 99.0 degrees Celsius is added to 100 grams of water at 25 degrees Celsius in a well-insulated container. After the system reaches thermal equilibrium, the temperature of the water is 28 degrees Celsius. What is the mass of the aluminum block? The specific heat capacity of aluminum is 0.9 joules grams to the -1, kelvins to the -1, or I guess you could write it as this. Okay, so for this problem, we're given initial and final temperatures, and we're also given a specific heat capacity. So that points us to this equation that's given on the equation sheet. It looks something like this, which we can use to solve this problem. However, this kind of equation that you're given on the equation sheet only deals with one object or one type of substance and one mass, but we can kind of manipulate this. If you understand this equation and what it means, we can manipulate it to make it work for two objects. In this case, there's water and there's also the aluminum block. And we're also given that it's in a well-insulated container. That's important because we can set the Q, or the heat energy of aluminum block, is equal to the negative of that of water. And if you rearrange this, you can get both of them on the same side. So you can get something like this is equal to 0. And again, we can set it equal to 0, or you can solve with this variation of the equation because it's a well-insulated container. So in a well-insulated container, we're assuming that there's no heat that's being added from the surroundings to the system, and vice versa, no heat is being kind of removed from the system. So both the heat that's gained and lost by both of the objects in the system should add up to 0. So now that we have established that, we can kind of rewrite this equation and solve and plug in and solve for the mass of the aluminum block. So Q is equal to mc times delta T, and delta T is equal to the final temperature minus the initial temperature. In this case, since we're adding the water and the block together in the same sort of container, the final temperature is the same for both, and that's going to just be the final temperature of the water, which is 28 degrees Celsius. So TF is equal to 28 degrees Celsius. TI for aluminum is 99 degrees Celsius, as it's stated here. Mass of water is 100 grams here. And then the TI, the initial temperature of the water, is 25 degrees Celsius. So TI water equals 25 degrees Celsius. Now you might be wondering, well, the specific heat capacity has kelvins in its units, so shouldn't we be kind of converting all of the temperatures to kelvins? And that's a good point. I want to say that you could convert everything to kelvins just by adding 273.15 to each temperature that you're given, but you don't have to, because since we're adding a constant to each temperature, when you subtract the temperatures, it's going to be the same thing. So for example, if you have TF of the final temperature for both water and aluminum is 28 degrees Celsius. Let's say you add like 273 to that, right? And you're also adding 273 to this 99 degrees Celsius, which is the initial temperature of the aluminum. Then when you subtract the TF from the TI, or I should say the initial from the final, or if you subtract TF minus TI, it's still going to be the same thing, since you're just adding the same amount of 273.15 to both temperatures. So we could, in this case, just keep everything in Celsius just to save us some time. So now that we established that, we should probably rewrite this equation again with these terms, and then we can go from there. So the Q sub aluminum is going to be the mass of the aluminum times the specific heat of aluminum, which we are given here, times the final temperature, which actually is the same for both the water and the aluminum, minus the initial temperature of the aluminum. I'm going to move this a little bit. We do the same for water, so it's going to be the mass of the water times the specific heat of water times the final temperature, which is the same for both, minus the initial temperature of the water. And all this is still equal to 0. So now we can pretty clearly see that our only unknown variable is this mass of the aluminum block. So we can just plug in everything else and then solve for the mass. So mass of the aluminum times this specific heat times the temperature, the final temperature, minus the initial temperature, plus the mass of the water, which is 100 grams, times the specific heat capacity of water, which I think should be given on the equation sheet, but it should be 4.184 in the same units as what were given for aluminum. And then the same final temperature, so 28, but then minus 25 as our initial temperature of the water. So if you do this and you just plug everything into the calculator, simplify and all of that, you should get that the mass of the aluminum is approximately equal to 19.64 grams. And that looks like option C. So our answer is C. Question 13. Calculate delta H reaction for the following reaction after it is properly balanced with the smallest whole number coefficients. Useful information is provided below. So when we're asked to find the delta H reaction for a reaction, you probably have located this handy equation on the equation sheet that you're given. It looks something like this, where the delta H reaction is equal to the sum of the stoichiometric coefficients times the delta H formation of products, subtracted the same sort of thing, but for the reactants. But as you can see, this n here, this variable, refers to the stoichiometric coefficients of each of the products and reactants, and we can't solve this problem immediately without first balancing the equation. So we need to do that first. So a good way that I like to start with balancing equations is to locate atoms or elements that only appear once on both sides. So in this case, we see that carbon only appears once on both sides, as well as hydrogen. So we can start with either carbon or hydrogen, but I typically like to start with carbon because it's just a larger atom, and I just like to do it that way. So we can start with carbon. And we're also asked for the smallest whole number coefficients. And since we have this subscript of 3 on this side for carbon, whereas CO2 only has 1 carbon, we should probably start with the smallest number of carbons possible on this left side. So we can just add 1 in front of this C3H8. And since we have 1 times 3, or 3 carbons on this side, we need to make sure that the carbon dioxide on the other side also has 3 carbons. And that's easy since we only have 1 carbon per mole of carbon dioxide, or not mole, but like 1 carbon per molecule of carbon dioxide. So we can just add a 3 in front of this carbon dioxide. So next we can look at hydrogen, because then again, hydrogen also only appears once on both sides. So we can start with the same process that we just did with carbon. So looking at C3H8, 1 times 8 gives us 8 hydrogens on this left side. So we need 8 hydrogens on the right side. And the only way to do that is to put a 4 in front of this H2O. And that's because this is the only molecule where hydrogen appears on the right side. And 4 times 2 equals 8. So that's balanced. And lastly, we have to look at oxygen. So this one is a little trickier, which is why I left it for the last part of this balancing equations thing, because we see that CO2 and H2O both contain oxygens. But since we already did most of the easy work first with the carbons and hydrogens, this shouldn't be a big issue. So we just kind of multiplied the subscripts with the oxygens times the coefficients in front of them. So 3 times 2 gives us 6 oxygen atoms in the CO2, and then 4 times 1, or I guess if you don't see a subscript, it just means 1. That gives us 4 oxygens from H2O. So this gives us 10 oxygens total. And we need to make sure that we have 10 oxygens total on the left side as well. And the only way to do that is by putting a 5 in front of this O2, because 5 times 2 gives us 10. So now that we have balanced this equation, we can go ahead and solve this problem. So delta H reaction is equal to the products minus the reactants. So the products, we have a quantity of 3 times the CO2. So CO2 is over here, 3 times negative 393.5 plus 4, because we have this coefficient of 4 in front of the H2O. Then we just subtract the same thing that we just did, but for the reactants. But in this case, you might notice that the delta H formation for O2 is not given to us, and that's fine because this is a combustion reaction. So the O2 isn't going to affect anything because O2 is in excess, because we're just reacting one type of molecule, in this case C3H8, with a bunch of O2. So the O2 doesn't really affect anything, so we're just going to subtract the coefficient of C3H8 times the delta H formation of that molecule. So that's just 1 times this quantity, so negative 104.7. And if you plug all this into your calculator, you should get negative 2043 kilojoules. And this matches up with option B, so the answer is B. Question 14. What is the electron configuration of Fe2+? How does the size of Fe2+ compare to the neutral Fe atom? So in this question, we're given a table of different choices, and the easiest sort of way I like to approach these types of questions is just by process of elimination. So I like to start with the size comparison because that's just mostly conceptual, and as long as you understand that, you can't get it wrong. So I want to start with that and then kind of work my way down through the process of elimination. So whenever we see a cation of the same atom or the same identity of atom, so in this case we have the cation of positive 2 charge iron versus the neutral iron atom, the cations are going to have the same number of protons as a neutral atom. Because remember, if we're changing the number of protons, you change the atom entirely. So it's going to be a different element. But in this case, it's the same element. So the number of protons is the same. However, cations have fewer electrons, and anions, which are the negative ions, have more electrons. So in this case, we have a positive iron cation, which means that it's going to be smaller because we have fewer electrons, but the same number of protons in the nucleus. So kind of like each proton can exert a more greater magnitude of attractive force to the remaining electrons. So that's going to be smaller. So right off the bat, we can eliminate 2 answer choices. So it can't be C and it can't be E, because C and E state that the Fe2+ size is larger than Fe, which is not true. So now we have to look at the electron configuration of the cation. to figure out which one is the answer. So the first thing we should probably do is locate where iron is, and that is over here. We also know that it has a 2+ charge, so it's going to be isoelectronic with an element that is like 2 atomic numbers behind it. So we have 26 for iron, so it's actually going to be isoelectronic with element number 24, which is chromium. So we're looking at chromium to figure out what the electron configuration of this cation is. And we also notice that these are all written with the noble gas configuration, so we can't eliminate anything from that since they're all the same. We have starting with argon, so we can just start with that. And for this type of problem, you should probably remember the SPDF blocks on the periodic table, but just as a recap, this part should be the S block, this part is the P block, this kind of metal area, this is the D block, and this area is the F block. So we can just kind of go and work our way down from there. Starting with the noble gas configuration of argon, we have 2 elements in the 4s block, so 4s2, and then we have 1, 2, 3, 4 elements in the D block. But remember, since we're in the metals, it's actually going to be 3d4 and not 4d4, because D is kind of like one level behind or one shell behind of S and P. However, metals also have a special property where these electrons in the s orbital, they can jump down to the lower level of 3d because it's just more stable. Because think about it this way. So basically an s orbital, there's only one orbital and it can be filled with these 2 electrons. So this is 4s, and then 3d, which has 3 orbitals, and they start filling out like this. We have 1, 2, 3, 4, right? However, this is kind of unstable because the most stable configurations will either have 3d, where something like this, where they all only have 1 electron, or it's going to be a totally full 3d orbital like this, or basically all orbitals are full. So these 2 are going to be kind of preferable orbital configurations for metals. And in this case, since we see we have 2 electrons in the higher 4s orbital, and we have 2 empty spots for electrons in the lower 3d orbitals, we can just move these electrons down, and this is going to give us a more stable configuration. So instead of 4s2 and 3d4, we're going to actually move this 2 over here and then get rid of this higher energy orbital, or this higher energy subshell of 4s, and then we're going to have 3d6. So our answer is going to be D. This configuration is going to start with argon and then 3d6, and the Fe2 plus ion is smaller than Fe. So our answer is D. Question 15. Using the average bond energies given below, estimate the enthalpy of combustion of 1 mole of propine, C3H4. Hint, first determine the Lewis structure of propine, and then write a balanced equation for its combustion. So a combustion reaction is pretty much just a reaction of some substance, in this case propine, with oxygen. And the typical sort of general combustion reaction formula is going to look like this, where you have a substance plus something moles of O2, and then that's going to turn into CO2 and H2O. So in this case, this substance that we're kind of investigating is propine, so that's C3H4, and this is our unbalanced equation for the combustion reaction of propine. So we have to figure out how to balance this equation. We're already given a kind of a hint because this question asks us for the enthalpy of combustion of 1 mole of propine. So that means we can start by putting a coefficient of 1 in front of the propine molecule. And just like the previous problem, or 2 problems ago, the way I like to approach these problems that involve balancing chemical equations is starting off with the atoms or the elements that only appear one time on both sides. So in this case, we should probably start off with carbon because it kind of seems obvious to me that it only appears once on both sides, once in propine on the left, and then once in CO2 on the right. And we already established that we have to put a coefficient of 1 in front of propine. So now we already know how many carbon atoms has to be on the left, and then that has to equal the amount of carbon atoms on the right. So 1 times 3, that's going to give us 3 carbon atoms on the left. So we need to do the same on the right, and the easiest way to do that is just put 3 in front of this CO2. Next, we can look for the hydrogen atoms because, once again, it only appears one time on both sides. So we can start with the same process since we know we have to use 1 mole of propine. We have 4 hydrogens on the left side, so we need to make that match on the right side. The easiest way to do that is to put a 2 in front of this H2O molecule because 2 times 2 equals 4 hydrogens, and then that's going to match on both sides. And lastly, we have oxygen. So on this right side, we have 3 times 2 or 6 oxygens from CO2, and then 2 times 1 or just 2 oxygens from the H2O. So that gives us 8 oxygens total. And we need to make that match on the left side as well. So 4 times 2 is equal to 8, so we can just write 4 in front of the O2. So now that we have this balanced chemical equation, which if you're not sure, you can check it on your own, but we have this balanced chemical equation, and the next thing this hint tells us is to determine the Lewis structures of propine, and obviously also O2, CO2, and H2O, but those you should already know. But anyways, for propine, a little bit of wisdom from organic chemistry is that anything with this "ine" ending means that it's going to be a triple bonded carbon. So that's just kind of a little bit of a cheat code, if you will. And anyways, we can kind of approach the Lewis structure in the same way that you just approached it in general. So we should start off with finding the numbers of valence electrons in the total number of valence electrons in the entire molecule. So we have 3 carbons, and carbon has 4 valence electrons, so 3 times 4, and then we have 4 hydrogens, but hydrogen only has 1 valence electron, so just plus 4. That gives us 12 plus 4, which is equal to 16 electrons. So now that we have these 2 kind of hints kind of established, we can draw out some Lewis structure and then check if it makes sense. So in this case, carbon should be our central atom because we will never use hydrogen as a central atom because carbon obviously can form 4 bonds, whereas hydrogen can only form 1. So we have 3 carbons, and that tells us that it's probably going to be the 3 carbons in the center. So we can draw something like this. We know that propine, this "ine" ending, means that one of these at least has to be triple bonded. So I'm just going to put this on the right side, and we know that it can't be there can't be 2 triple bonds because if we put triple bonds on this left side, that wouldn't work out because then we would violate the octet rule since carbon likes to form 4 bonds. So this looks good for our central sort of like molecule part. And now we have to add the 4 hydrogens. So we can use the same property of carbon wanting to form 4 bonds to figure out where to place these hydrogens. So if we have the triple bond on the right side, that means there's only going to be room for 1 hydrogen on the right side for this right end carbon to have 4 bonds total. That means that the remaining 3 hydrogens must be on the left side, like this. And just to check, we have 1, 2, 3, 4 bonds for this carbon on the left side. We have 1 and then 3 bonds, which is 4 bonds for this central carbon atom. And then we have 3 plus 1, 4 bonds for this right side carbon atom. So this is our propine structure. And a good way to check that is to just go back to the number of valence electrons total that we solved for earlier. So each bond has 2 delocalized valence electrons. So it would be 2, 4, 6, 8, 10, 12, 14, 16. And that checks out with our previous calculation. So this should be the valid Lewis structure of propyne. You can repeat this process for the other molecules involved in the combustion reaction, namely O2, CO2, and H2O. But since you should already know those Lewis structures, I'm just going to write that down. And you can pause the video and do it on your own if you want or not. But anyways, O2 should look like something like this, where we have just a double bond between these 2 oxygens. CO2 should be a linear, sorry, we should probably change that. CO2 is a linear molecule that looks like this. H2O, which you should be very familiar with, looks like this. And the reason you need to draw out these Lewis structures is because it helps us determine how many types of each bond there is in this reaction. So if you remember the enthalpy equation, which I think should be given on your formula sheet, but if not, it's pretty basic. But basically the enthalpy is equal to the sum of the energy of the reactants minus the sum of the energy of the products. And by sum, it just means like the coefficient of the equation times the number of bonds of each type in these molecules. So let's kind of plug that in. I'll just move this a little bit so that there's more space. Okay, so we can start by plugging in some values, which is given in this table. So we have reactants, we have this C3H4. So we have one triple bonded carbon bond, which is going to be 839 kilojoules per mole, so 839. We have one CC single bond, which is 347 kilojoules per mole. And we have 1, 2, 3, 4 carbon-hydrogen single bonds. So that's going to be 4 times 413 kilojoules per mole. And that's going to be our energy for this reactant, the C3H4. We also have to find the energy for the O2 from the combustion reaction. So we have 4 O2s, and each O2 has this single or this one double bond between oxygen and oxygen. So we just put 4 times 498. So that's going to be our sum of energy for the reactants, and we have to subtract from that the sum of the energy of the products. So let's do that. Starting with CO2, this is the structure of CO2. So we just see that there are 2 equivalent CO double bonds. And since we have 2 double bonds per molecule of CO2, but we have 3 CO2s, we can just write 6 times the energy for the CO double bond, because we have 3 CO2s times 2, that would be 6. So we have 6 times 799. And then for not for hydrogen, for water, we have 2 water molecules, and each water molecule has 2 OH single bonds. So that's going to be 2 times 2, or 4 times the energy for the OH bond, which is 467. And if you plug that into your calculator, you should get negative 1832. It should be kilojoules per mole. And that matches up with answer choice B. So our answer for this question is B. 16. Which one of the following is the best Lewis structure of bromate anion BrO3-? So for this problem, we're just given a bunch of possible Lewis structures, and they all look pretty similar, with bromine as a central atom and oxygen as the atoms around it, which makes sense because oxygen is it's in the period above bromine, I think. So it will be the more electronegative atom. So it's going to be on the sides, whereas bromine will be the central atom since it's the least electronegative. So because all of these structures look pretty similar, we can just kind of go through and do process of elimination. So the way I like to think of it is look for the formal charges. So we know that this overall charge should add up to 1 minus, or just a negative charge. And we see that in all of these brackets, right? But we have to make sure it actually matches what's inside the brackets. So starting with A, we know that bromine is in group 17 or something like that. So it will have 7 valence electrons. And then oxygen has 6 valence electrons. And that's going to be pretty much what we need to know for finding the formal charges of each of these atoms in each of these Lewis structures. So starting with the oxygens, since they're probably easier, I guess, we've seen them a lot. For choice A, we have these 2 oxygens, or actually 3, that both have 2 lone pairs and 2 bonds to the central bromine atom. So they're all going to have the same formal charge. So let's do that. So oxygen here will have 6 valence electrons minus 4 2 lone pairs, or 4 non-bonding electrons, because each lone pair has 2 electrons, and then 2 bonds. So 6 minus 4 minus 2, which is 0. So all of these oxygens are going to be neutral, so they're not going to have any formal charge. And in this case, we have to also look at the bromine to make sure to see if it matches this -1 charge overall. So bromine has 7 valence electrons. It has 1 lone pair, so that's 2 non-bonding electrons, and has 2, 4, 6 bonds. So, 6 bonds. So there's 7 minus 2 minus 6. 7 minus 2 is 5. 5 minus 6 is -1. And this means that our overall charge is -1. So that does check out. So A is still a possible Lewis structure for now. We can repeat this same process for all the others. So for B, we know that these 2 oxygens, like in the process we just did for A, will be neutral. And then for this oxygen, we can do it again. We have 6 valence electrons. We have 3 lone pairs, which is 6 non-bonding electrons, and we have 1 bond. So 6 minus 6 minus 1, that's -1. So this oxygen has a -1 charge. And then for the bromine, we have 7 valence electrons. We have 5 bonds, and we have 0 lone pairs, so 0 non-bonding electrons. So this is going to be a 2+ charge. So this has a 2+ charge. 2 minus 1 is going to be a +1 charge, and that does not match up with this -1 charge that we should have overall. So B can be eliminated as not our answer. So for C, the same thing happens. We know that this double bonded oxygen is neutral, and these 2 single bonded oxygens have a -1 charge like we established in B. And then we can just figure out the charge for the bromine. So again, we have 7 valence electrons. We have this lone pair, so 2 non-bonding electrons, and we have 1, 2, 3, 4 bonds. So 7 minus 2 minus 4. 7 minus 2 is 5, and then 5 minus 4 is 1, or 1 plus. So this bromine is going to have a +1 charge. And this is a valid structure because we have 2 negative charges and 1 positive charge, so that does add up to a -1 charge overall. So C is still possibly one of our answers. So we have to move on to D. Again, like we established previously, these 2 double bonded oxygens are neutrally charged, and this single bonded oxygen has a -1 charge. For this bromine, though, we have 7 valence electrons minus 2 electrons in a lone pair, and then minus 5 bonds. That's going to give us 0. So this bromine is also neutral, and we just have this -1 charge on this oxygen. So this is possibly still going to be an answer choice because negative, negative, it matches up. Finally, for E, we have these 3 single bonded oxygens, so they all have a -1 charge. We can recalculate the charge for bromine. So we have 7 valence electrons, we have 2 non-bonding electrons in a Sloan pair, and we have 3 bonds. So this is going to be 7 minus 2 minus 3, 5 minus 3, that's 2 plus. So this bromine will have a 2 plus charge. So -3, well, -1 times 3, because we have 3 -1 charges plus 2 positive charges. That does add up to a -1 overall charge. So this can still possibly be our answer. So we've eliminated B, but we still have 4 answer choices to go through. And that's kind of maybe, it might be daunting, but pretty much there are some tricks. So first of all, we want to find one of the Lewis structures where the negative charge is sitting on the more electronegative atom. So negative charge on more electronegative atom. In this case, it's oxygen because, like I said previously, bromine is, I think, like 1 or 2 periods below oxygen. And as per periodic trends, the right side of the first 2 periods are more electronegative. So oxygen is a more electronegative atom in this case compared to bromine. Second of all, we want to reduce the formal charges overall. So reduce magnitude of formal charges. So what this means is that something like in the Lewis structure in option E is going to be sort of not the most ideal because we see that all of these atoms in this molecule has a formal charge that is not 0. So we want to find a Lewis structure that has a negative charge on the more electronegative atom and has the least amount of overall non-zero formal charges on all the atoms combined. And so that points us to answer choice D, because as you can see, if we go down the list again, for A, we have the lowest amount of formal charges just as much as D because we only have this -1 charge. However, in A, it's on the bromine, which is on a less electronegative atom. So that's not going to be the preferable Lewis structure. For C, it's kind of just the magnitude of formal charges. We have 3 out of the 4 atoms has a formal charge that isn't 0, and we could make it better, so it's not going to be C. And then it's not going to be E for the same reason, because all 4 of these atoms has a non-zero formal charge. So the only answer left is D. So the answer for question 16 should be D. Question 17. Using the information below, which choice would be the best estimate of the average bond length, keyword average, in the carbonate anion, CO3 2-. So for this question, it's basically asking for a weighted average of bond lengths because we're given this table of average bond lengths for each type of bond that might occur in this anion, and we're asked for the average bond length. So it's just a weighted average. But to first be able to do that, we have to figure out what this anion looks like, because we need to figure out what it looks like to be able to know how many types of each bond there are. So to do that, we need to find the Lewis structure of this molecule. And to start with, the way I like to start with Lewis structures is to first figure out how many total valence electrons it should have. So we know that carbon has 4, and then oxygen has 6. So 6 times 3 oxygens is 18. And we also have to add 2 more valence electrons because of this 2- charge. So if we add it all together, 4 plus 18 plus 2, it should give us 24 valence electrons total. And then we have to figure out which one is going to be our central atom. So in this case, the only contenders are carbon and oxygen. And oxygen is obviously a pretty electronegative atom, so it's not going to be the central atom, because the central atom is the least electronegative atom, and in this case, it should be carbon. So we can draw a structure sort of like this, preliminary structure, and then kind of figure it out from there. Another important property of carbon is that it likes to form 4 bonds. So we need to add another bond to one of these CO bonds to make sure that this carbon has a full octet of 4 bonds. So you can add it to any of these 3 oxygens, but I want to put it on the top one just so it looks kind of nice and symmetrical. And now we can fill in the lone pairs and then see if they match up with this number of valence electrons we determined. So whenever we see one single bond, we have 3 lone pairs or 6 more localized electrons. So these 2 oxygens on the bottom are going to have 3 lone pairs. And then this top oxygen, which has 2 bonds, will only have 2 lone pairs to make a full octet. And you can count this just to make sure. But yeah, this is how it should look like. And we can check now to make sure that this matches up with the 24 electrons we determined. So each lone pair has 2 electrons, and each bond has 2 delocalized electrons. So if we count them, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we do have 24 electrons, so that means there's no other adjustments we need to make to this Lewis structure, so that's good. However, we do notice that this anion should have a 2- charge, and that's going to come from these 2 oxygens at the bottom, because if we remember that oxygen has 6 valence electrons, 6 minus 6 non-bonding electrons, or 3 lone pairs times 2 electrons in each lone pair, and then minus 1 for this 1 bond will give us a -1 charge. So these 2 will have a -1 charge. Whereas this oxygen at the top also has 6 valence electrons. It has 4 non-bonding electrons and then 2 bonds. So this is going to be 0. And this will be a neutrally charged oxygen atom. So the overall Lewis structure will have a total charge of 2-, and that does match up with what we're told in the problem. So now that we have a valid Lewis structure for this molecule, we can determine the average bond length. So we see that there's 1 C double bonded to oxygen bond, and we have 2 single CO bonds. So we can kind of do that. And the formula for a weighted average should be the average bond length is equal to 1 times the double bond that we found, and then 2 times the single bond over the total number of bonds. And in this case, you might be thinking, oh, isn't it 4 bonds because we have 1, 2, 3, 4. But actually, this double bond should be considered as 1 double bond rather than 2 single bonds. So we actually have a total number of 3 bonds. So if we plug in all of these numbers from the table, you get that it's 1 times 123 plus 2 times 143 divided by 3 total bonds. And that should give us around 136.3. And that tells us that answer choice D is our correct answer. 18. How many of the following molecules have all of their atoms in the same plane? So plane, same plane, that just means linear or planar. So that could be trigonal planar or square planar configuration for the molecular shape. So we just have to go through all of these and pretty much draw out the Lewis structures to figure that out. So for this first molecule, we already sort of see it in a Lewis structure. So we have a good hint. It's going to look something like this. The only change we're making is we're actually drawing out the carbon and hydrogen bonds. And because carbon, both of these carbons have a full octet of 4 bonds, which is good. This is just going to be linear. And that's because we just see this double bonded carbon bond in the center. So all of these atoms are going to be on the same plane. Another way to look at it is not only do we have this double bond, which is linear, these two carbons, they're also all trigonal planar because we don't see any lone pairs and we see 3 bonding electron groups. So that's going to be trigonal planar for both. So all of these atoms are going to reside on the same plane. So let's circle that one. The second molecule we're looking at is F2O. And this one probably requires a bit more thinking since it's not really drawn out for us. So if we do the same process that we typically do for drawing out Lewis structures, first we have to figure out how many total valence electrons are there. So fluorine has 7, so 2 times 7, and then oxygen has 6 because it's in group 16. So 2 times 7 is 14, plus 6, that's 20 electrons total. And we also know that oxygen's pretty electronegative, but fluorine is actually the most electronegative atom on the periodic table, and that's because oxygen and fluorine both are on the same period, period 2, but fluorine is to the right of oxygen, so it's going to be more electronegative than oxygen. And so this means that oxygen will be our central atom since it's less electronegative. So we can start by drawing it out like this and then filling in the lone pairs starting from the outer atoms, which are the fluorines. So to create a full octet for something with just 1 bond, we can add 3 lone pairs, like so. And then we can check, this is 8 plus 8, so that's 16 electrons, which means we need 4 electrons on the oxygen, or 2 lone pairs. And all of these molecular shapes mostly just depend on the molecular geometry of the central atom. So in this case, it's oxygen. And we already know that this is not going to be planar because it has a very similar structure to the water molecule, which we know is bent because it has 2 bonds and 2 lone pairs. So this is bent, and it's not going to be planar, so it's not going to be in the same plane. We can repeat the process for H2CO. So H2CO, hydrogens have 1 electron or valence electron each. Carbon has 4, oxygen has 6. So if we add all of these together, we have 6 plus 6 is 12 electrons total. And we know that carbon is going to be our central atom most of the time because, well, oxygen is very electronegative and hydrogen will never be our central atom since it can only form 1 bond. So we can draw out carbon and we could draw out the general shape. It's going to look something like this. And keep in mind that carbon wants to form 4 bonds. And we can't add an extra bond to any of these hydrogens since it would violate the octet rule. So we have to put the double bond with the carbon and the oxygen bond. And this looks good because now that we have a full octet for carbon, hydrogen, and hydrogen, we need to think about the valence electrons that we're adding to the oxygen. So we have 1, 2, 3, 4 bonds, and each of these bonds has 2 delocalized electrons, so 4 times 2, that's 8. So you can subtract 8 to get 4 electrons. So we need 2 lone pairs, or 4 electrons, on this top oxygen atom. Okay, so now that we have that established, we can look for the molecular geometry. So, like I said, molecular geometry pretty much just depends on the central atom. In this case, it's carbon. And we can see that there are no lone pairs on this carbon atom, and we have 3 bonding electron groups. So this is going to be trigonal planar, and it's going to be planar. So all of these atoms are on the same plane. So this is one of our planar molecules. For NH3, we can do the same thing. We know that nitrogen has 5 valence electrons, and 3 hydrogens means 3, so 5 plus 3 is 8 valence electrons. And because hydrogen can never be our central atom, the central atom is going to be nitrogen. So our general sort of Lewis structure is going to look something like this. Now we can check to make sure if we need to add more electrons to the central atom or not. So each of these bonds has 2 delocalized electrons, so 3 of them is 6, which means we need to add 1 lone pair or 2 electrons to the central nitrogen atom. And so this gives us all we need to know. So looking at this nitrogen, we have 4 electron domain groups because we have these 3 bonds, and we also have this non-bonding lone pair. However, because we have a lone pair, it's not going to be trigonal planar. It's going to be trigonal pyramidal. So this is trig pyramidal, which is not planar. So this is not going to be a planar molecule. So that's not going to have all the atoms in the same plane. CO2, we can repeat this process. Well, you should know what CO2 looks like, but basically carbon has 4 valence electrons, and each oxygen has 6. So that's going to be 4 plus 2 times 6, or 4 plus 12, which should be 16 electrons. Carbon is going to be our central atom because remember that oxygen is very electronegative, and it wants to form 4 bonds. So we can just kind of put it like this, and we have 4 bonds, so that's 8 electrons. So we have 8 left that we need to fill in. Since carbon already has a full octet, we just fill in the oxygens, so we can put 2 lone pairs on each oxygen for a total of 16 electrons. So that's our Lewis structure, and once again, this carbon is really all we care about, and we don't see any lone pairs, and it just looks like a line. So that's going to be linear because we have these 2 bonding electron groups and no lone pairs, and linear means it's also all the atoms are on the same plane. So CO2 is also going to be a planar molecule. I'm going to move all of this a little bit for some more room, and then we will do the last 3. Okay, we can repeat this process with BeCl2. So beryllium, I think, has 2 electrons. I need to double check on that, but anyway, I think it has 2 valence electrons, and then chlorine has 7, but we have 2 of them, so 2 plus 14 is 16 electrons total. Chlorine is pretty electronegative, so we can assume that this beryllium is going to be our central atom. So we can write something like this. Oops. Start filling in the lone pairs on the peripheral, or like the atoms on the sides, to see if they match up to this 16 electron total that we have. So now that we have a full octet for these 2 chlorines, which this is just 8 and 8, we do have 16. So this is going to have no difference, so we don't have to add any more lone pairs to this central beryllium atom. So now we can kind of think about the molecular geometry. And once again, just like CO2, it's going to be linear. And that's because we don't have any lone pairs on this central atom. We just have 2 bonds, or 2 bonding groups of electrons. So this one will also be a planar molecule. For SO3, we do the same thing. Sulfur has 6 valence electrons, and then each oxygen has 6, so 6 plus 18 gives us 24 total electrons. And you can kind of see that oxygen is very electronegative, so sulfur is probably going to be our central atom. So we can draw a preliminary structure like this. However, if you remember, sulfur can expand octet. So an oxygen wants to make 2 bonds, so we can add another bond to all of these and then fill in the remaining electrons. So if we have 2 bonds, this is 4 electrons, so we need 4 more on each oxygen for a full octet. So we can just add 2 lone pairs to each oxygen. And so each oxygen sulfur bond, this will have 8, 8, and 8. So that gives us 24, and there's no difference. So that's all we have to do for this Lewis structure. And looking at this central sulfur atom, it has 3 bonding electron groups and no lone pairs, which means it's trigonal planar. So this is going to be another one of our planar molecules. So this will be circled. And then lastly, we have PF5. I'll put it over here. PF5. I don't remember exactly how many valence electrons phosphorus has. I think it's 5. And then I know that fluorine has 7. So 7 times 5 is 35. So 35 plus 5, that's going to give us 40 total electrons. But phosphorus, just like sulfur, has the capability for an expanded octet. So we can just draw it out with fluorine as our edge sort of atoms, because remember, fluorine is our most electronegative atom in the whole periodic table, so it cannot be our central atom. So we can start drawing like this and just filling in all of these lone pairs. So if we have a single bond like such, we have to add 3 lone pairs for a full octet. So if we put all of these lone pairs in, like this, now we have 8, 8, 8, 8, 8. So we have 5 times 8, which matches up with 40 electrons, so there's no more work we need to do here, which means that we don't need to add any lone pairs to the central atom. And because this phosphorus is a central atom and it has 5 bonding groups of electrons and no lone pairs, it's going to be trigonal bipyramidal. And this is not planar because it has bipyramidal in its name. It's not a planar molecule. So this is not a planar molecule. So the only molecules that have all their atoms in the same plane are these ones that are circled. And you just add up all of these, which gives us 5. So the answer should be C. 19. Arrange the following unbranched molecules in order of increasing vapor pressure at room temperature: pentanol, ethanol, propanol, and butanol. So the way I like to remember the vapor pressure trend is that it's inversely proportional to boiling point. So for boiling point, basically the stronger bonds are going to be harder to break, and then they're going to consequently have a higher boiling point. So basically, ionic bonds are harder to break than polar covalent, which are harder to break than nonpolar covalent. So this ionic bond will have a higher boiling point. Nonpolar molecules will pretty much just have a lower boiling point because they're just easier to break apart. So vapor pressure is kind of the opposite of that. So ionic will have the lowest vapor pressure, whereas nonpolar covalent will have the highest vapor pressure. But that doesn't really matter for us because we see that these are all unbranched molecules and they're all very similar in structure. They're just all unbranched alcohols. So another thing we need to consider is that within these nonpolar covalent bonds, we have London dispersion forces. And basically, to determine which type of nonpolar covalent molecule has a higher boiling point or a higher or lower vapor pressure than another one, we're just looking at the mass. Because if you think about it, the more massive a molecule is, even if it's equal on all other levels, like the types of bonds and types of intermolecular forces with the other molecules you're comparing it to, the more massive molecule is still going to be harder to break. So it's going to have a higher boiling point than the other smaller molecule. And that's because these London dispersion forces add up. So we're just basically looking for ranking these molecules in order of size. So in order of size, we just look at these prefixes. So if you remember, basically, eth means 2 carbons, and then prop means 3 carbons, but means 4 carbons, and then pent means 5 carbons. That one's probably pretty obvious. So we just want to order these in order of size. And because vapor pressure is the opposite of, or like the trend is the opposite of boiling point, this means that the smallest size molecule is going to have the highest vapor pressure, but it will have the lowest boiling point. So basically, we want to see that ethanol is the highest and then pentanol is the lowest. And we just kind of order it like this and just kind of see which one matches up. So obviously, the rightmost molecule has to be ethanol because it's the smallest. So it cannot be A, B, or E. So it's between C and D. So we know that pentanol is the largest molecule of these molecules. So it's going to be the first one, or it's going to have the lowest vapor pressure. So our answer should be C. 20. Arrange the following molecules in order of increasing boiling point. So for this question, it's probably a good idea to recall the general trend of boiling point. So boiling point general trend goes like ionic and hydrogen bonds. Hydrogen bonding and ionic compounds have the highest boiling point because they're the hardest to break and have the strongest bonds. And then it's going to be the polar covalent bonds, and then it's going to be the non-polar covalent bonds / molecules. Whoops. Okay. So now that we know that, we can kind of try to eliminate some of these. We know that H2O out of all 4 of these molecules is the only molecule that can participate in hydrogen bonding. So that's going to obviously be our highest boiling point. So that eliminates B and E. And the reason why H2O is the only molecule out of this set of molecules that can hydrogen bond is because in order to hydrogen bond, the hydrogens have to be bonded to either fluorine, oxygen, or nitrogen, or Photon atoms, I guess, if you want to call it that to remember it. But none of these other molecules have any of these Photon atoms bonded to the hydrogen. So our H2O is going to be the highest boiling point. The rest of these are all also polar covalent, just like water or H2O. And because they're all polar covalent, we can't just use that to eliminate or kind of order them in terms of boiling point. We have to look at the London dispersion forces. So London dispersion forces happen in all compounds, or I should say molecules, whether they're non-polar covalent or polar covalent or ionic. However, it also increases relative to the mass of the compound or the molecule. So if you think about it, the greater the mass of the molecule, the more London dispersion forces are in that molecule, and so it's going to add up and just be harder to break. So those more massive molecules will have a higher boiling point than the less massive molecules. And to figure out which ones are more massive and which ones are less massive, we have to look to the periodic table. In the periodic table, you'll see that for these other 3 that we still need to order, we see that oxygen is on the second period. Then we have sulfur, Se, and Te. So this means that the mass increases down the periods, or, if you look at one group, as you go down, the mass will increase. So our second highest boiling point should be H2Te. So let's write this down. Our massive molecule is H2Se, which will have our third highest boiling point. And then our lowest boiling point should be H2S. So that matches up with answer choice A. So our answer should be A. Question 21. Which substance contains exactly 2 pi bonds? So for this question, basically the way I like to approach it is to draw the Lewis structures. And because we're only dealing with carbons and hydrogens and nothing else, we can kind of skip a lot of the steps that we usually want to take with drawing Lewis structures. because I guess in this class, like, you'll never really see a carbon with more or less than 4 bonds, so you'll never see a lone pair on a carbon, and hydrogens can only form a single bond with anything, so we can kind of just skip all of those like previous steps and just kind of guess and check Lewis structures. So starting with A, we have C2H4, and we know that carbon has to be the central atom because hydrogen can never be the central atom. So we can draw 2 carbons like this, and then put 2 hydrogens on each side for 4 hydrogens total. However, this is not a complete Lewis structure because, as you can see, both of these carbons only have 3 bonds, and both of them want 4 bonds. And the only way to do that is by adding another bond to this carbon-carbon bond, because we can't add a double bond anywhere else, because hydrogen can only form a maximum of 1 bond. So this is going to be our Lewis structure for C2H4. And as you can see, we only see this 1 pi bond. It only has 1 pi bond, so this cannot be our answer. For choice B, we have C3H8. And the only way to make this really work, if we follow the same steps of putting the carbons in the center, the only way to make this work with carbons, with all of the carbons having 4 bonds, is by putting 3 hydrogens bonded to the carbons on both sides, and then 2 hydrogens bonded to the central carbon atom. Because now you'll see that there's 3 here and 3 here, which gives us 6 hydrogens, plus the 2 in the middle, which gives us 8. And we can't really add or subtract pi bonds, because if we add a double bond to any of these carbons, we're going to have to remove some of the hydrogens. And that's not okay because we need to keep 8 hydrogens, and that's pretty much the maximum we can get with the single bonds. So this is our Lewis structure. And as you can see, we just have single bonds, so we have no pi bonds. So B cannot be our answer. For option C, we have C2H2, and we can sort of follow some of the same logic as we did for A. We have 2 carbons, so these have to be in the center. And we also have 2 hydrogens, so we can put the 2 hydrogens on each side to make this symmetrical. And then, as you can see, these 2 carbons only have 2 bonds, and it wants to have 4 bonds each. And the only way to do that is by adding 2 bonds to this CC bond, like such. So now both of these carbons have 4 bonds each. You might be thinking, okay, but this has only 1 pi bond and 1 triple bond. But actually, this has 2 pi bonds and 1 sigma bond, because we have this sigma bond, which is this single bond, and then we have these 2 additional bonds, which correlates with 2 pi bonds. So we can write 2 pi bonds for C, and just like that, we know our answer is C. But just to go through the rest of these molecules, we can kind of follow the same logic again. So for D, C2H6, we can put the 2 carbons in the center, and the only way to make this work is to put 3 hydrogens on each side. Otherwise, the carbons will not have a full octet, and the hydrogens won't match the number that's in the subscript. And this, as you can see, it's similar to B. It doesn't have any double bonds. So this has no pi bonds and cannot be our answer. And finally, for E, we have C3H6. So we have this 3 carbons in the center, and we have 6 hydrogens. So we can start with what we have for B and then sort of remove hydrogens as we kind of like count them. So we can add all of these hydrogens in to give us 8, and then try to remove 2 hydrogens by adding some double bonds. So let's say we want to add a double bond to these 2 carbons here. Then we have to remove some hydrogens, right? Because this carbon now has 5 bonds, and this one also has 5 bonds, which violates the octet rule. So we have to remove 1 hydrogen from the center carbon atom, and also 1 from this carbon atom on the right. So now we have 3 plus 1 is 4 plus 2 is 6 hydrogens. So this could be a valid Lewis structure. However, we see that the only way to make this work is to only add one pi bond over here. So that can't be our answer. Because if we add another pi bond like here, we have to remove 2 more hydrogens, and then we'd have 4 hydrogens instead of 6. So that can't be it. So the answer to this question is C. Question 22. The formula of acetone is provided below. Which row in the following table correctly describes acetone? So this is kind of like a simplified Lewis structure, but in order to answer this question, since we're given non-ideal angles, as shown by these less than and greater than signs, we have to add some lone pairs to be able to figure that out. So with these CH3 groups, we don't have to do anything because the carbons won't have any lone pairs since they have 4 bonds, and hydrogen can only form 1 bond. So we just have to add the lone pairs to this oxygen. And to do that, we know that each of these 2 bonds has 2 delocalized electrons. So we have 4 delocalized electrons here, and the oxygen has to have 4 more electrons to fill an octet. So that means it has to have 2 lone pairs, like such. And now we can sort of answer this question. So starting from the left side of this table, we can figure out the molecular geometry around the central carbon atom. And because this carbon atom doesn't have any lone pairs, and it just has these 3 bonding electron groups, it's going to be trigonal planar. So we already know that the answer cannot be B, C, or E. So between A and D is the answer. The second thing is the number of lone electron pairs, and as I said previously, the only atom in this molecule that has lone pairs is going to be oxygen, and that's going to have 2 lone pairs to fill an octet. So we already know the answer is going to be A because in answer choice D, it says that there are 3 lone pairs, which is wrong. But just to make sure you understand everything, let's just go through the rest of these criteria just to make sure. So because of these lone pairs, even though it's trigonal planar and approximately 120 degrees between all of these bonds, it's actually going to be slightly greater than or slightly less than 120 depending on which one or which angle you're looking at. So if you think about it, these lone pairs on this oxygen are going to push these the CCC bond closer together. So the CCC bond angle should be slightly less than 120 degrees, and then the CCO angle should be slightly greater than 120 degrees. And because not all of these atoms in this molecule are the same, and also we have a very electronegative atom, oxygen, with lone pairs, we're going to have a dipole moment moving this way, or a net dipole moment moving that way. So we don't have a non-zero dipole moment. So again, our answer is A, because that's the only one that matches everything that we just said. So the answer for question 22 should be A. 23. Which row of the following table contains the correct information about vinyl cyclohexene, C8H12? So we're given this carbon skeleton structure, and we're asked immediately how many sigma and pi bonds there are. And you might just think, oh, okay, I'm just going to count these bonds, right? But then we don't have all of the hydrogen and carbon bonds sort of accounted for in this structure. So a good first thing to do when you're given a carbon structure like this is to draw in the hydrogens. So we have 2 hydrogens here because this carbon can only have 2 more hydrogens to form a full octet or 4 bonds. We have 1 here because the carbon already has 3 bonds, and then same here. And then for this carbon, it has 2 bonds to carbons, so it can form 2 bonds with hydrogens. Same thing here. For these 2, since there are 3 bonds to carbons adjacent to it, both of these carbons can only bond with 1 hydrogen. And then for this last carbon, since it has 2 bonds already, it can form 2 more bonds with hydrogens. So now that we've drawn out all of these bonds, we can count them. So starting with the sigma bonds, we just have to count the number of bonds in total without counting these double bonds twice. So if we start with just the basic carbon skeleton structure bonds, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 CC bonds, or I would say sigma bonds. And now we have to count the bonds between carbon and hydrogen. So we have 2 here, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So we have 12 carbon-hydrogen sigma bonds. And we have to add these together to get the total number of sigma bonds in this molecule, which is 20. So because we already have that established, we can eliminate some of these answers. So our answer choice has to be between A and D. So B, C, and E are eliminated. The next thing we want to look at is the number of pi bonds, and that's just the number of double bonds in this molecule, which is pretty obvious. We only see 2, so we can't eliminate anything further from that since both A and D have 2 pi bonds. Next, we have to look at the number of sp3 hybridized carbons. An sp3 hybridized carbon is pretty much just a carbon that is tetrahedral or it has 4 bonds. So we're looking for or counting the number of carbons in this molecule that has 4 bonds. So four different bonds, 4 bonding groups, not 4 bonds in particular, but 4 bonding groups. So the only ones are going to be this carbon, this carbon, this carbon, and this carbon. So we have 4 sp3 hybridized carbons, and then we have to look at the sp2 hybridized carbons, which is just the number of carbons with 3 bonding groups. And that's just going to be this one, this one, this one, and this one. Or I guess I'll just circle them with open circles. Because a double bond counts as 1 bonding group instead of 2. So we also have 4 sp2 hybridized carbons, and the only answer choice that matches with that is answer choice D. So our answer is D. Question 24, which functional group is not present in the following compound? So a good way to kind of solve this problem is to just circle and label all of the functional groups that are present in the compound, and then just eliminate the one that isn't in the compound. So if we go from left to right, we see that there's an alkene here, which is just a carbon-carbon double bond. So it can't be A. We see 2 oxygens, so this is going to be an ester. It's not an ether, because if it was an ether, it would just be this oxygen. But since we have a double bonded oxygen right next to it, it's going to be an ester. So it's not choice E either. Then we also have an amino group or an amine group. So it can't be C, and the reason why it's an amine is because if you see any nitrogens, it's pretty much going to be an amine. And then lastly, we have a OH and a double bonded oxygen. So this is a carboxylic acid. And so D cannot be our answer. So that leaves us with choice B. Just to sort of clarify, you might think that there is an alcohol in this compound because of this OH group, but just like with ethers versus esters, we don't count them as both. So we don't count this as both an ether here and an ester overall. And just like that, we don't count this as an alcohol and a carboxylic acid. We look for the biggest group that specific functional group is a part of. And the carboxylic acid is going to be that bigger group. So it doesn't have an alcohol. The alcohol group is part of the carboxylic acid, and we only count the carboxylic acid. So our answer has to be B. 25. Order the following functional groups from the most to least number of carbon-oxygen bonds. So for that, we just kind of have to memorize these functional groups and what they look like. And just a good recap is to draw their Lewis structures. We don't really have to do lone pairs and all of that, since we're just focusing on the number of CO bonds. So starting with ketone, a ketone looks like a carbon-oxygen double bond with two R groups. So these can be anything. Most of the time, you'll just see them as just carbon and hydrogens and stuff like that in a longer carbon chain. But this is what a ketone looks like. So it just has this one CO double bond. But since we're just looking at or looking for the number of carbon-oxygen bonds and not like specifically pi bonds or sigma bonds, we can count this double bond as two CO bonds. Our next functional group is esters, and esters are kind of like ethers and ketones combined. So we're going to have this similarity with this CO double bond, but we're also going to have a oxygen single bonded to the carbon that is double bonded to this other oxygen. And like before, we're going to have two R groups like such, and this means that we have the two CO bonds from this double bonded oxygen and then one from this single bonded oxygen. So we have a total of 3 CO bonds in an ester. Next, we have amines, and amines have no carbon-oxygen bonds, and that's because an amine is just a carbon bonded to a nitrogen and some number of hydrogens, depending on whether it's anionic or cationic, whether it's like a positive charge or negative charge or neutral. So this has 0 CO bonds. And lastly, we have alcohols, which are just OH bonds, and then this O is bonded to a carbon. Or I guess it could be bonded to anything else, but in this case, it's probably asking for carbon and oxygen bonds. So in this case, it would just be a carbon, oxygen, and a hydrogen. And this only has 1 CO bond. So now we can rank these in order of the number of carbon-oxygen bonds. So esters should have the most carbon-oxygen bonds. So we can eliminate A, C, and D. And we're just between B and E because we know that esters have the greatest number of carbon-oxygen bonds. The second greatest is going to be the ketone because we have this double bond, which counts as 2 CO bonds. So we know that the answer is E because this has ketone as our second, and then B has alcohol as our second, which should be third. So our answer for this question is E. 26. Which of the following monomers is used to produce the addition polymer shown below? So for addition polymers, basically the monomers have a double bond, and then that double bond opens up and becomes a single bond so that the carbon double bond that is now a single bond, the carbons can bond to something else, and that's how it bonds to repeat units of the same monomer. So essentially what we're doing in this problem is taking out these two bonds and then adding a double bond over here. So whichever answer choice matches up with that is going to be our answer. So as you can see, it's pretty obviously going to be C. So our answer is C. And just as another demonstration of why this double bond opens up, once it opens up, these two carbons on the side, so this one and this one, can now form these two bonds to the same monomer just linked up together. So that's why our answer should be C. Question 27. Styrofoam used to make disposable coffee cups is composed of polystyrene, a polymer with a general formula shown below. What is the average molecular weight of polystyrene for which the degree of polymerization is 44,000? So basically what this question wants us to do is to find the molar mass of this repeat unit or monomer in the styrofoam polymer, or I guess polystyrene, and then multiply it by 44,000. And just so you know, because we're finding the molecular weight of polystyrene, which is a polymer, since we're given a degree of polymerization that is not 1, we do not want to make the mistake of adding the double bond and then removing these bonds. Because when we're bonding all of these monomers together, the double bond will have already opened up to just be this single bond with these two single bonds to the adjacent same monomer so that they can link up and become a polymer. So we just want to find the molar mass of this indicated region right here. And to do that, there's a couple steps we need to do first, because half of this structure, like this ring over here, is given as a carbon skeleton and not a full Lewis structure. So we have to add some hydrogens into this structure so that we can get the correct molar mass. So the way we do that is just by counting the number of bonds that carbon already has, and then subtract that from 4, and that's going to be the number of hydrogens bonded to that carbon. So for this carbon right here, we have 1, 2, 3 bonds already, which means there's only going to be 1 hydrogen bonded here. And the same pattern continues throughout this ring, because all of these carbons, except for this one, I guess, but all of these other carbons have 3 bonds already, so they're all going to just have 1 hydrogen bonded. However, this carbon over here already has 4 bonds. As you can see, it's bonded to this carbon, and then there's 2 bonds to this carbon. So this is our full Lewis structure. So now we can just kind of add up all of the molar masses of all of these elements and then multiply it by 44,000 to get our answer. So we have to count the number of carbons and hydrogens, which make up this monomer. So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons, and then we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So we have 8 of each, and carbon is approximately 12.01 grams per mole. And then I think hydrogen is about 1.008 grams per mole. So you just multiply the 8 times both of these quantities and then multiply it by 44,000. So something like this, or I guess if you want to rewrite it, meter should look like this. 8 times 44,000. And if you plug all of this into your calculator, you should get 4,582,336 grams per mole. And this looks pretty similar to answer choice D. So our answer for 27 is D. 28. A photon of which wavelength will excite the HCl stretching vibration in hydrogen chloride? Recall that the visible portion of the electromagnetic spectrum is between 400 to 800 nanometers. So this is kind of just a memorization question. You're not given this diagram. I just kind of copy and pasted it from the internet, but it's good to have it memorized. But anyway, if you don't have the diagram memorized, there is a trick, sort of, and that is that all of these stretching vibrations are not going to be visible to the naked eye. So that means that it's automatically not going to be B or C, so it will be between A and D. So if you don't have anything memorized from this spectrum, you can just take a 50-50 gander at these types of questions. However, even though it's not visible, we know that these stretching vibrations are only excited by infrared radiation. So infrared sits over here, and it's between 10,000 nanometers and around 500 nanometers. So the only answer choice that corresponds with that is answer choice D. Because if we look at A, 153 nanometers, that's around the ultraviolet range, and that's not it. So the answer for this question is D. 29. How many peptide amide bonds are in this chain of amino acids? So if you know what a peptide or an amide functional group looks like, basically this question is just asking us how many there are in this molecule. So recall that a amide looks like this, where we have an amino group or an amine, and we also have this carbonyl group, or in this case, it would be sort of like a ketone. But combined, this is going to be our amide. So we just need to count the numbers of these in this chain of amino acids. So here we see there's one, and then we see there's another one here, and there's no more in this chain. And this means that our answer should be C, or 2 amide bonds. Question 30. Which of the following molecules has an infrared spectrum shown below? Consider only those peaks labeled in the spectrum. So this is basically a functional group identifying question in disguise. So we just have to figure out which one of these answer choices has the functional groups that is shown in this infrared spectrum. So we only see a CH stretch and a CO double bond stretch and a CO single bond stretch. And because we have both a CO double bond and CO single bond, this means we have an ester. And an ester looks sort of like this, where we have a carbon, and then we have this single bond, this CO single bond, and this CO double bond. And the only sort of answer that matches up with an ester is going to be D. So our answer is D. 31. Which class of molecules do 1, 2, 3, and 4 belong to? So this is just a functional group identifier sort of problem in disguise, because once we can identify the functional groups in each of these molecules, we can pretty much figure out what class they belong to. So starting with 1, we see that there's amino groups or amines. We see that there's these carboxylic acids, and we see that there are amide bonds. So these amide bonds are going to be the reason why this molecule is a peptide. And as you remember, single amino acid monomers, or just single amino acids in general, have a side chain, a carboxylic acid, and an amino group. So that checks out. For 2, we have these 2 ring structures, and whenever we just see ring structures with alcohols in them, it's pretty much always going to be a sugar. And in this case, since we have 2 rings, it's going to be a disaccharide. For molecule 3 up here, we see that there's a phosphate group, we have a sugar ring, and we have 1/2 of a base pair. So that's going to be our nucleotide. And lastly, for molecule 4, we see that there's also a phosphate group, and we also have these 2 very long hydrocarbon chains, which are relatively nonpolar. So we have a polar head over here, as indicated by this phosphate group with a negative charge, and also this nitrogen with a positive charge, and we have these 2 tails, which are pretty much just very nonpolar. So this is going to be our phospholipid. So 1 is a peptide, so it can't be B or E. 2 is a disaccharide, so it's not D. 3 is a nucleotide, so it has to be C. So our answer for question 31 is C. 33. Ethylene glycol C2H4OH2 is the main component of antifreeze used in automobile radiators. What mass of ethylene glycol in grams must be added to 1.00 liters of water to lower the freezing temperature to negative 10 degrees Celsius? And we're given the Kf of water is 1.86 degrees Celsius divided by the molality. Okay, so we have this equation that's in our equation sheet, which looks like this, where the delta TF just means the change in the freezing temperature. KF, we are given that, and then M, or little m, refers to molality, not molarity. So molality is basically mass over mass, whereas molarity would be mass over volume. So in this case, molality is going to be the number of moles of solute divided by the number of kilograms of the solution. So the solute is going to be the ethylene glycol. So this is the solute. And the solution is the water. So water is the solution. And 1.0 liters of water, that's the same as 1 kilogram of water when you convert it to the mass. And we're also told that we have this Kf of water. So we have all of these except for the molality. So the first step we can do is solve for the molality. So if you plug in all of these numbers into this equation, the change in the freezing temperature, or the absolute value of the change in freezing temperature, since molality cannot be negative, is just the absolute value of negative 10 degrees Celsius, or just 10, and that's equal to 1.86 times the molality of this solution. So if you divide both sides by 1.86, you get molality is equal to approximately 5.3763 moles of ethylene glycol, over 1 kilogram of water. So, but we're asked for what mass of ethylene glycol must be added. So we need to find the mass in grams, and to do that we need the molar mass of ethylene glycol. So on your exam, you'll have to add up all of the molar masses from all of these atoms to find the total molar mass of ethylene glycol. But to save time, since it's a pretty simple calculation, I'll just give it to you, which I looked it up, and it should be about 62.07 grams per mole. We're also told that it's 1 liter of water, so we can kind of just get rid of this, or I guess we can do it in a dimensional analysis type of way, but 1 liter is equivalent to 1 kilogram. So if we do some dimensional analysis, we take our molality that we solved for here, so 5.3763 moles of ethylene glycol divided by 1 kilogram water multiplied by 1 kilogram of water, because we are asked specifically what mass is added to 1 liter of water, or 1 kilogram, which is equivalent. And we also have to multiply that by the molar mass of ethylene glycol. So we have 62.07 grams over 1 mole. And to check that we did this step right, we just need to make sure everything cancels out so that we're only left with grams as our units. So if we cancel out moles and the kilograms of water, we do get this gram as our final unit. So if you plug all of these numbers into your calculator, you should get approximately 333.7 grams of ethylene glycol. And that's pretty similar to what we see in answer choice C. So our answer is going to be C. 34. What is the total molarity of dissolved ions in a solution containing 296.6 grams of MgNO32 per liter of solution? So note that in this problem, we're asked for the molarity of dissolved ions, not just for the molarity of this solution, or I mean, not solution, but this molecule in general. which means there's going to be an extra step in the dimensional analysis of this problem. So the extra step is basically figuring out what amount of ions this ionic compound is going to dissolve into when it's placed in a solution. And it's pretty easy to do that. We see that there's a quantity of NO3 or nitrate here bonded to this magnesium, and there's 2 nitrates. So we have 2 nitrates plus 1 magnesium, which gives us 3 total ions. We're also given that we need to find the molarity of 296.6 grams of this molecule specifically. So we need to convert everything into moles by finding the molar mass of this molecule. And then after that, we have to multiply it by 3 because there are 3 total ions that it dissolves into. So the molar mass, in your exam, you're going to have to do it by hand just by adding the molar masses of all of these component atoms. But that's a pretty simple calculation, so I'm just going to skip forward and tell you what it is. A quick Google search will tell you that the molar mass is equal to approximately 148.315 grams per mole. So now that we have all of this information, we can set up a simple dimensional analysis calculation. So we're starting with the given amount of 296.6 grams of MgNO3 and we're multiplying this by the molar mass to convert everything into moles. So we're going to put the number of moles on the top, so 1 mole over 148.315 grams of MgNO3, 2, because this way the grams will cancel out and we will get our intermediate sort of number in moles, which is what we want. And then we have to do the second step, which previously established that we need to account for the number of ions that it dissolves into, not just the amount of MgNO3 in this solution. So we just multiply this by 3 moles of ions for 1 mole of MgNO3, and then these cancel out. So we get our desired unit, which is the moles or the number of moles of ions. So if you plug all of that into your calculator, you're going to get approximately 5.99939 moles of ions. And since it's just asking per liter, which we assume is 1 liter and not 2 or 3 liters or any other number, we can just divide this by 1 liter to give it to get this answer expressed in molarity instead of just numbers of moles. And that's just going to be 5.99939 because anything divided by 1 is just itself. And that's approximately equal to 6. So our desired, or I mean the total molarity of this solution is going to be 6 m. So it's going to be C. 35. For the phase diagram of carbon dioxide below, estimate the pressure needed to liquefy CO2 at room temperature. So CO2 is originally going to be a gas. So we're looking for something along this line between the liquid and the gas. And this is a pretty simple question. Basically, we just locate where 20 degrees Celsius is on the x-axis and then find the corresponding pressure on the y-axis that is on this line. So 20 degrees Celsius on the x-axis is around here. So if we draw a line vertically from there and then draw another line from there horizontally, it's going to be between 50 and 60 atmospheres of pressure, and the only sort of answer choice that matches that description is answer choice D, or 55 atmospheres. So our answer for this question should be D. 36. A normal blood cell is removed from an isotonic solution, which is a solution with the same osmotic pressure as the cell, and placed into pure water. Which one of the following best describes what happens to the cell when it is in pure water? So if you remember from osmosis, basically, if we have something like this where we have a cell and we have some sort of pure liquid around the cell, and let's say the cell has some particles of solute inside of it. Basically, the water is the only thing that can move, or I guess the liquid in this case, because the solutes are too big to move through these semi-permeable membranes. So it's just going to be the water that is moved. And so the water is going to move into the areas, or from the areas of low concentration of solutes to the areas of high concentration of solutes. Because if you look at it this way, this cell has a very high concentration of solutes, and the water has no solutes. And since water is the only thing that can move through the cell membrane, it wants to move in a way that will relatively balance out the concentration of solutes both inside and outside of the cell. So in this case, water will rush into the cell, or I guess in this example, and we're going to have something where the cell is much larger, it's full of water. It will have the same number of solutes because the solutes are too big to pass through the membrane, and then the water level outside of the cell will be lower. So that's going to be kind of the general concept for this question, but we have a specific scenario. So the specific scenario is this normal blood cell is initially in an isotonic solution, which means that there are the same number of solutes, or I guess the same concentration of solutes in both the outside of the cell and inside of the cell. So this is our example, and this is our situation. It's kind of hard to draw concentrations of solutions, but a good way I like to do it, or I like to think about it, is to just draw the same number of solute particles in both. So if we have a cell like this, let's say it has 4 solute particles inside the cell. In isotonic solution, it will have sort of like similar or 4 particles outside the cell as well. And this is all balanced, which means that the cell is kind of in a nice healthy state. It's not swelling, it's also not wilted or very like small. So this is our isotonic solution, and we're transferring it and placing the cell into pure water. So we're going to put the cell into a container with pure water. So the cell will still have the same number of solutes because the solutes are too large to pass through the cell membrane. However, the pure water will not have any solutes. It's just water. So in this case, it's similar to our example, where if you have a bunch of water around the cell, which is less concentrated than the solutes inside of the cell, the water is the only thing that can move. So the water is going to rush into this cell in order to balance the concentration between the cell and the surrounding water. So in this case, something like this is going to happen as a result. And as you can see, the cell is going to swell up. Eventually, it's going to burst, and the cell will be no more. So the only answer choice that kind of lines up with that is answer choice E. 37. Paper chromatography was used to separate a mixture of 2 molecules, squarane and circlane. The separation of the 2 molecules during paper chromatography is shown below. So we're given these 3 different images of what the plate looks like at different times. And just to let you know, paper chromatography is the same thing as TLC analysis or thin layer chromatography, which you have done in the lab. So we should probably start off with a little bit of conceptual background into what TLC is and what it does and how it works. So in TLC, we have 2 phases. We have the stationary phase, and we have a mobile phase. So the stationary phase is just this sort of solid thing that's on each of these plates. Whether you put the solvent on or not, it is always just on the plate by default, and it's going to be solid, and it's usually going to be silica gel. And silica gel is a polar compound. So if we're using a polar compound as our stationary phase, we need a liquid mobile phase that is nonpolar in order to separate the compounds that we're analyzing in terms of polarity. So now that we have that established, let's look at these images. So on our initial chromatography paper, nothing has happened yet because we haven't really added the mobile phase. So all of these compounds are starting in the same position. And then as time goes on, the solvent or the mobile phase starts to move up the paper and takes these particles or these molecules with it. And because our mobile phase is nonpolar, if we think about it, the more nonpolar molecules are going to move up further on the plate. So in this case, these circles are going to be more nonpolar, and these squares are going to be more polar. Because if you think about it, the like substances mix with like substances. So a nonpolar mobile phase is going to mix in better with nonpolar particles or nonpolar compounds and take those further up the plate when time passes. So now that we have that established, we can look at these answer choices and sort of eliminate some of them. So we know that the square is more polar than the circle, so we can already eliminate C and D. And basically, the choice is between A and B, and we have to figure out the retardation factor or the retention factor. So the retention factor is just the distance traveled by each of these types of compounds divided by the total distance. And as you can see, something that travels further is going to have a larger sort of ratio or retention factor. So these circles are going to have a higher retention factor than the squares. So the only thing that matches up with that is answer choice B. So our answer for this question is B.